Okay, we're going to start one of my favorite topics in all of calculus called related rates. And you should, at this point, be fairly comfortable with implicit differentiation. That's where y is not explicitly defined, so whenever we take the derivative of a y term, we have to tack on dy dx, because the differentiation is happening with respect to x. An implicit, a related rates problem, it's basically a word problem that we solve using implicit differentiation, and the derivatives are taken with respect to time, because a rate or a speed has to do with time. It's how fast something is happening. So we need to use implicit to take what's called a derivative with respect to time. So instead of dy dx, we're going to have d whatever dt. So the time variable is a third variable that we do not see in our equation, but it just shows up in the little chain rule part of the implicit differentiation. So I know that the derivative of x squared is 2x. Now, if I was doing the derivative with respect to x, I would just move on to the next part, because my dx is just 1, and we've talked about how that doesn't actually show up because you don't have to do the chain rule if it's an x part. But now we're differentiating with respect to time. So the derivative of x squared is 2x dx dt. Okay, and the derivative of y squared is 2y dy dt. So whatever the variable is, x, y, or it could be r for radius or h for height, we'll get a lot of geometric type formulas, it's d that letter over dt. And the derivative of 16 is still 0, so I don't need to multiply that by anything. But this is the idea of derivative with respect to time. Now we're going to make this x squared plus y squared, this formula, stand for something. That's where the word problem comes into play. But first, make sure you're comfortable with taking the derivative with respect to time. Whatever letter it is, whatever variable it is that you're using, d that letter over dt needs to accompany your derivative. Okay, so I've got a little, want to show you a little bit of a graph in motion. Let's graph a circle, kind of like the one we just had on the last slide. X squared plus y squared equals, let's just call it A, and I'm going to let that A be a slider, and it's going to go from 0 to 25. That'll give me a radius of 5, and let's get these set up so I can push play. So this moving circle is an example of something that might happen in a related rates problem. It might be, we'll have to try to come up with a word problem setting that creates a moving circle. It might be you tossed a stone into a pond and you see the ripple moving outward. It might be, like an oil spot on a driveway creeping its way outward. But it's a circle. If you think of this in 3 dimensions, this could be like a sphere, a balloon that's blowing up. But related rates has to do with the motion, the change over time of some sort of shape like this. And think about it, as the reason these rates are related is because you've got different things going on. We've got a radius that's increasing from 0 out to 5. We've got an area that's increasing. And those speeds of how fast those quantities are changing are related to each other. Okay, so just imagine, keep this picture in mind for our next problem. We're going to have a circle that's changing, and we're going to talk about how fast the area is changing is connected to how fast the radius is changing. Okay, so we have a circle. I'm not going to give it any context right now about the pebble or the oil spot or whatever. Let's just keep it simple and start with a circle. A circle is expanding such that the area is increasing at a rate of 2 square inches per second. So every second we're adding 2 to the area of this circle. So I want to start out by just pointing out that this 2 is dA dt. It's how fast the area of the circle is changing. That given quantity is something we're going to plug in just a minute. So the way you want to start these problems is always with a formula that's always the case. So in this case, it's going to be the area of a circle. And when I mean this is always the case, this happens no matter what the size of the circle is, no matter how fast the area is changing, no matter that we're talking about when the radius is 10 in just a minute. This is the area of any circle. This is always true. So write down an equation that's always true. Now differentiate that equation with respect to time. So the derivative of A with respect to time is 1 dA dt, or just dA dt. All right, this expression means derivative of area with respect to time. This is how fast the area is changing. In just a minute, we're going to plug in a 2 there. Okay, so remembering that pi is a constant, the derivative of pi r squared is 2 pi r. Okay, I'm just dropping the 2 down and decreasing it to a 1. The pi is just a constant that's along for the ride. However, since this is with respect to time again, dr dt. Okay, so this is always true also. This is always true for any circle that is changing its radius. The area is changing, the radius is changing. This is always true. At this point, we're going to move to what I would call like the snapshot. We are going to look at one specific instance, and that's when the radius happens to be 10. Remember our changing circle from the last slide. At some point, it's 10. And at that instant, that snapshot time, the rate of change of the radius and the rate of change of the area are going to be related to each other, and we're going to use that to solve this. So how fast is the radius changing? Our question, how fast is the radius changing, dr dt. How fast something changes is d that thing over dt. So dr dt is my unknown. So that's the only thing I don't have, and I can plug in everything else. dA dt equals 2 pi, both constants. R is 10, okay? I'm plugging in this constant to go from something that's always true to something that's true just at an instant. And dr dt is my unknown. So if I can isolate dr dt, I have solved for the question, how fast is the radius changing? Okay, so this is not a difficult equation to solve. I'm going to divide both sides by 2. And don't forget that that creates a 1 on the left. I'm going to divide both sides by 10 and by pi. So the solving is the easiest part once you get it set up. So my answer is 1 over 10 pi. And you could type that in a calculator and get a value. But at the instant when r is 10, assuming that the area is changing at a rate of 2, the radius is changing at a speed of 1 over 10 pi. Now the givens could be different. I could have given you dr dt and asked you for dA dt, and that just depends on the physical properties of the situation. Are we talking about an area that's changing at a constant rate, or are we talking about a radius that's changing at a constant rate? And either one of those could be the case. All right, so there's our first good, solid example of a related rates, and let's do one more. Okay, so every related rates chapter in every calc book in the world has questions about ladders sliding down walls. And I thought that was just kind of a made-up thing until one day I was on a ladder that was sliding down a wall. Remind me and I'll tell you all about it. But in this case, we have a 10-foot ladder sliding down a wall. So imagine here's the wall, here's the ground, and we have a 10-foot ladder propped up against it. And much to the dismay of the person standing on this ladder, the bottom starts sliding out and the top starts sliding down, and this person is afraid for their life. So this, on the last problem, the kind of always true geometric formula was the area of a circle, because we had a circle that was changing. In this case, we have a triangle made by the wall, the floor, and the ladder. So let's write an equation that involves a right triangle, and you know the best equation to involve the sides of a right triangle is the Pythagorean theorem. Let's write an equation that's always true. I need variables, and I need variables for the quantities that are changing. I'm going to use x and y because we usually use x and y for horizontal and vertical distances. So I'm going to call the distance from the floor to the top of the ladder y, and the distance from the base of the wall to the bottom of the ladder x. And think of an equation that's always true that involves these quantities. All right? X squared plus y squared equals 10 squared. You can make it 100, it doesn't matter, because we're getting ready to take the derivative of it anyway. But this is always true. Okay? No matter how far the top of this ladder slides down, it's always going to follow this pattern. Okay? So this is always the case. Now I want to take the derivative of this. The derivative of x squared 2x dx dt. The derivative of y, 2y dy dt, and the derivative of 10 squared, which is 100, is 0. Okay, so now let's plug in our givens and we'll have our answer. Now at this point we're going to go to the snapshot. Okay, this is only true at one instant, and what is that instant? When the bottom is 8 feet from the wall. Okay, so there are 4 quantities, and I need to figure out 3 of them and solve for the 4th one. So one thing I know is that the bottom is moving 3 meters per second away from the base of the wall. So if you think about this arrow down here, 3 meters per second is the speed at which this spot is moving, which means x is increasing at a rate of 3. And we talked about how the speed at which something changes is d that thing over dt. So the one thing I know I can plug in right now is that dx dt equals 3. I'm going to leave a space. Actually, I'll go ahead and plug it in when the bottom is 8 feet from the wall. So we're talking about the moment when x equals 8. So 2x equals 8, dx dt equals 3, plus 2 times y times dy dt. Now it looks like I'm missing something because dy dt is the question. How fast is the top of the ladder sliding down the wall, which is dy dt. But I'm missing y. I don't know y at this point. Okay, so here's what we do about this. And the more complicated these problems get, the more detective work you're going to have to do to fill in all the missing parts. In this case, we want to look to the always true statement to figure out what y is. So no matter what, x squared plus y squared equals 10, correct? So if x happens to be 8, then 8 squared plus y squared equals 10 squared. And you might recognize that as a Pythagorean triple 6, 8, 10. So what I know is that y is 6 because at this instant, the triangle is a 6, 8, 10 right triangle. Okay, so some way we've got to figure out all but one of our unknowns. And in that case, that's how we figure out the 6, by looking at the always true statement. And now we just need to solve. 2 times 8 times 3, that's 24 times 2, that's 48, plus 12 dy dt equals 0. So that's 12 dy dt equals negative 48. And I'll divide both sides by 12. Dy dt equals negative 4. And that would be in meters per second. Now, before we finish this up, think about why that quantity is negative. Dy dt is negative 4 meters per second. All right, can you think about why? If you look at y, which is this distance here, at the moment we're talking about where this ladder is sliding down the wall, y is decreasing. So when things change, if they're negative, those quantities are getting smaller. If they're positive, those quantities are getting bigger. So that's why our answer makes sense to be negative. All right, so we're going to stop with the related rates with 2 good examples. They will get a little bit more complex, but let's get good at the simple ones first before we move on.